In this video, I'm going to talk about Hooke's law. Along the line, we're going to discuss stiffness, stress, strain, and the Young's modulus. This video is focused on stressing the difference between stiffness and the Young's modulus. So let's get started. Consider a given material, let's say this is a rubber, whose initial length is L1. So let's take the initial length of this rubber as L1, and let's say this material has a cross-sectional area of A. So the area we are talking about is the area of this circle, right? Now let's apply a force on this material. And if we do that, the material, let's assume it stretch to this level. So now we have a new length of L2, right? And here we have the force acting in this direction. According to Hooke's law, if we measure the extension E, which is the difference between the second length and the first length, according to Hooke's law, the force acting on this material is directly proportional to the extension. So this means if we increase the force on this rubber, we directly increase the extension. If you decide to remove this sign of proportionality, you're going to get F equals to KE, where K is known as the stiffness, otherwise known as the force constant. So this is what Hooke's law is all about. It's a law that tells us the relationship between an applied force and an applied force and the extension. This time around, the force we are referring to is a longitudinal force. So it tells us the relationship between the force and the extension, where K is the stiffness. The value of K can be calculated given the force and the extension. So I'm going to show you Hooke's law in action using the Mavinhub physics lab. So let's take a look at what we have here. Before applying any force, that is, before hanging a weight on this spring, this is the spring which represents the material. Before hanging any weight, you'll see that the length of this spring is somewhere around 35. If we add some mass, you see that the spring extends by a given centimeter. As we increase the mass, in other words, as we increase the force, you can see that the spring extends accordingly or proportionally. As you keep increasing the mass, which means as you add more force, you extend the spring by a given amount. So this shows that the force is directly proportional to the extension. The force on this spring is given as the mass times acceleration due to gravity. So basically, if you happen to be on it, the force will be 320 times 10, which is roughly acceleration due to gravity on Earth. But have you wondered what would happen if you perform this kind of experiment on the moon, or let's say in Jupiter? So let's take a look at how this spring will extend in the moon and in the Jupiter. You can perform this kind of simulation using the Mavinhub physics lab. So let's take a look. Under the settings section, you can change the acceleration due to gravity to that of any planet within the solar system. And you can also choose that of the moon. If you can see from here, the moon has an acceleration due to gravity of 1.6. So let's take a look at how this experiment would behave if it were done on the moon. So let's check it out. Let's increase the mass. You'll see that the mass is growing, but the force isn't much because the force is whatever the mass is times 1.62. So the extension is very, very minimal, despite the fact that we have a relatively high amount of mass. So this is how the spring will stretch if it happens to be on the moon. So let's take a look at how it will behave on Jupiter. On planet Jupiter, let's pick Jupiter here. That of Jupiter is 24.8. Jupiter has a very high gravity, so the acceleration due to gravity is 24.8. So let's see how this experiment goes over there. If you increase the mass slightly, you see that the extension is really significant, even for a relatively small amount of mass compared to that of the Earth. You see that we've even gone way beyond 100 centimeters. So you can see that Hooke's law applies anywhere within the universe, but the difference here is the extension over there will be affected by the gravitational pull or gravitational force governing that planet or that satellite. So let's go back to our discussion on Hooke's law. Now that we know that the relationship between the force and the extension is given as follows, the question now is what really is the stiffness of a material? The stiffness is a measure of the resistance to deformation of a given material, which means if the higher the value of K, that is, if K goes up, it means the material will have a very high resistance to stretching or extension. So what that means is a material with a very high stiffness will not stretch that much, even for a very large amount of force. Whereas a material with a low stiffness will stretch significantly when a small amount of force is applied. So we can say that a very thick and heavy rubber will tend to have a higher stiffness compared to a very thin rubber. So stiffness is basically a function of the material, this cross-sectional area, and the length of the material. So I'm going to explain this in detail after talking about Young's modulus. So to talk about Young's modulus, we need to understand what is known as stress and strain. What is stress? Stress is the force per unit area. What that means is given a unit area of that material, if you divide the force applied by the area, you get stress. Then what about strain? Strain is the extension per length. So you can imagine a case where the original length is 1 and the original cross-sectional area is 1. If you have this kind of scenario, your stress will be similar to you applying the relation between stress and strain will be similar to you applying the Hooke's law. But then let's take a look at another idea called the Young's modulus. Young's modulus is stress divided by strain. So you can almost think about it this way. Stress is more or less like the force per area. Strain is extension per length. Then Young's modulus is a constant. So what we can see from here is Young's modulus is similar to the stiffness, although not exactly the same, but similar because if stress relates to force and strain relates to extension, then Young's modulus relates to stiffness. So let's write the Young's modulus this way. So it means Young's modulus is F over A divided by E over L1. So that means Young's modulus, we can write the whole thing as F over A equals Young's modulus times extension over original length. So this relationship connects the force per area with the extension per initial length. So the question now is, what's the relationship between stiffness and Young's modulus? Let's take a look at that in the next slide. From the previous slide, we know that K is equal to F over E. That's the force divided by the extension. And we know that force over area is equal to Young's modulus times extension over original length. If you make F over E the subject of the formula here, you're going to get F over E is equal to Y times A over L1. We can substitute F over E as K. So that means K is equal to Y times cross-sectional area divided by original length. So what this means is force constant is a function of the material, the resistance to deformation by the material, which is the Young's modulus, and it's also a function of the cross-sectional area and the original length. So what you can imply from this is Young's modulus is constant irrespective of the structure of a material, whereas stiffness is determined by the structure of a material. So let's take a look at this illustration. If you have these two rubbers, so let's say you have a rubber whose cross-sectional area is as described as this, and compare that with another rubber, the same length, but with a much bigger cross-sectional area. The question is, what will be the Young's modulus? So let's say Young's modulus of this is Y1 and Young's modulus of this is Y2. Both of them the same material. Will Y1 be the same as Y2? The answer is yes. Young's modulus will be the same as long as they are the same material. Then let's take a look at the stiffness. Let's say this is K1 and this is K2. Will they have the same value? The answer is no. K1 will be less than K2. So which means K2 will be greater than K1. So why is that the case? The reason is, given that the length is the same, the greater the cross-sectional area, the greater the stiffness. And that's why if you have a rubber that is really wide in cross-sectional area, if you try to pull that rubber, you tend to exert a lot of force to stretch it even by a small amount, compared to when you have a very thin rubber. If you have a very thin rubber, you can easily stretch it. If you have a very thick rubber, you can't easily stretch it. So the higher the cross-sectional area, the higher the stiffness. But the Young modulus is not affected by that. Now let's take a look at this other scenario. Let's say you have two beams. You must have seen beams that are used in construction sites, very long beams used in construction sites. Let's say you have this long beam. So let's say this beam is 10 meters, right? Then let's say you have a very small fraction of this beam, a very small fraction of this beam, and let's say this beam is 10 centimeters, right? You will notice that if you if you try to dangle this beam, it easily you can easily dangle this beam compared to this beam. So what that suggests is this beam can easily respond to a stretching force compared to this beam. And the reason is the longer the beam, the smaller the stiffness. That's why you can easily bend a beam that is quite long compared to a beam that is quite small. The reason is the stiffness of a long beam is lower than the stiffness of a very small beam because the stiffness is inversely proportional to the length. The higher the length, the lower the stiffness. So this illustrates that stiffness is not a constant for any shape of that material, whereas Young's modulus is constant irrespective of the shape. Stiffness is a function of Young's modulus, cross-sectional area, and the original length. So this explains clearly why in, most engineers tend to work with Young's modulus rather than stiffness, because stiffness is a function of the structure, the dimension, whereas Young's modulus is just constant for a given material. So let's take a look at some of the let's take a look at the Young's modulus of common materials. These are the Young modulus of common materials. You have rubber. Rubber has a very small Young's modulus. That's why you can easily stretch it. And if you go down, you'll see that the one with the highest Young's modulus in this list is steel. Steel has a very high Young's modulus, and that's why it cannot easily you can't easily stretch it, and that's why it's commonly used for it's commonly used in construction sites alongside with concrete. It has a very high Young's modulus. It doesn't easily respond to stretching force or longitudinal force. Doesn't easily extend when longitudinal force are applied when you apply longitudinal force to it. In summary, this video has explained clearly what Hooke's law is all about, and I've clearly explained how stiffness relates to Young's modulus, and I've clearly shown why engineers work with Young's modulus rather than stiffness.